yeah, so in the previous talk, like yesterday and also today, I learned a lot about about peridynamics and the general non-local models, and also we have already seen several talks regarding the applying the local boundary condition onto peridynamics and the general non-local models. So for example, the work by Francisco, by Zelda, by Burak, Patrick, and Robert. So I learned a lot from these works. Thank you. And yeah, so here I want to emphasize our main focus on this work is a little, so basically our main focus on this work is a little bit from some other works that we try to develop a complete workflow. So that combines basically the handling of the traction loading and also the evolution of the boundaries by breaking bounds and also by handling the Meshfree quadrature rules. So and also at the same time, we hope that still preserves the asymptotic compatibility. So, and also I want to emphasize this is the joint work with my student Huaiqian You, with my collaborator Nathan Trask from the Sandia National Lab, and also I want to thank my my founding support from NSF. So, okay, yeah, so here I'm going maybe to go fast about the introduction about the non-local model and the peridynamics. So peridynamics was originally introduced by Dr. Siling, and it provides a unifying mathematical framework to describe the material, to describe the mechanical response of the material and also the damage. So it's a unifying framework for both the damage region and the region without damage. So, and then the peridynamics is a non-local model. So therefore, like other non-local models, its natural boundary condition should be non-local. So, but however, like discussed in many previous talks, they are in many real-world applications. So for example, like the one shown on the left-hand side here, only the local traction loadings is available on a sharp interface. So for example, like in this example, that comes from one of our simulation. So there is a ring which is subjected to the interior pressure, and then this ring is going to expand, and finally the crack is going to develop on the edge, and then the ring will become fully fragmentation. So therefore, therefore to make the peridynamics model that more applicable to more real-world applications, we are hoping that we can develop a treatment to handle the complex traction loadings on the complex geometry. And on the other hand, we are hoping that we can still keep the nice property of peridynamics. So that means we hope that like peridynamics, it describes the model. It has a unifying mathematical framework for the damaged and undamaged region. So therefore, we hope our mathematical formulation for this traction loading is also a unifying formulation for the region for the material points, which is far away from the traction loading boundary condition and close to the traction loading boundary condition. So we hope to use one formulation to describe that. And on the other hand, we hope that we can combine that with the Meshfree discretization method because of its efficiency and its ease in handling the evolution of fracture. So, okay, so here are the desired properties of this development. So firstly, the domain decomposition. So the domain setting is as follows. So here we assume that on the red line, there is a traction loading applying on the sharp interface. And then on the blue line, we assume that we have the Dirichlet type boundary condition. So that means we have the information of the displacement fully available on this blue line and a thin layer outside it. So here, because the peridynamics model is consistent with the local classical continuum model when the horizon size goes to 0. So our idea comes from here that because the traction loading it's naturally a local type boundary condition. So therefore, we want to use the knowledge that our peridynamics model is consistent with the classical continuum model. So then we want to develop a proper non-local analog to the classical, the traction loading boundary condition. So, and then the second property we desire that is we want to combine that with a Meshfree discretization, because in the Meshfree discretization, it has the advantage. So the Meshfree discretization was originally discussed by Dr. Siling and Askari, so in 2005, and it has in the Meshfree discretization, all the when there is the evolution of the fracture. So the fracture surface can be sharply represented by the bond breaking. So that provides a efficient and also natural treatment of the fracture problem. So then the third property we want to preserve is the asymptotic compatibility. So that was also originally introduced by Xiao Chuan and discussed by her yesterday. So in this asymptotic compatibility, what we want to keep is as the horizon size and the discretization size. So basically what we call H here, we keep a constant ratio between them, and then we hope that when they goes to zero simultaneously, we can converge to the right local limit. So I think this is the so-called delta convergence that's discussed by Patrick also yesterday. So okay. So now what are the formulation we are looking at? So here we consider the linear peridynamic solid model, which we call LPS in short, as a prototypical state-based peridynamics model, although the idea might be extended to more complicated models. So the LPS model, the formulation for the momentum balance equation and the nonlocal dilatation is given by the following. So here we need to solve for the nonlocal displacement, so which is U here, and the nonlocal dilatation, which we represented by theta here. So when the horizon size delta goes to zero, this LPS model, the momentum balance equation, is going to converge to the Neve equation, and the LPS model is consistent with the linear elastic model. And then the nonlocal dilatation is consistent with the divergence of the displacement. So the local dilatation. So yeah, so then before we propose a formulation, let's try to see what are the missing part. So what is going on when the material point is nearby the sharp the traction loading boundary. So that is when it's in the red region here. So let's look into the horizon, what happened in the horizon of this material point. We can see that some of the integral, so basically represented by yellow here, is actually outside the computational domain. So those integral is actually missing. So therefore, we need to propose some modifications or maybe also estimates to fix this missing of the integral. So the first step, we propose a modification, a correction tensor for the nonlocal dilatation term. So this idea is actually inspired by the SPH method. So the idea is we develop a correction tensor as following, and then a corrected nonlocal dilatation operator theta. So this correction tensor, it guarantees that as far as our displacement is linear, then we are going to recover our corrected nonlocal dilatation is still going to recover the local dilatation, the corresponding local dilatation. And another nice property here I want to emphasize is, so here we can see that this nonlocal or this correction tensor, when it is actually given by the integral of basically the blue region. So when the material point X goes to the inside, so goes into the green region here, then this correction tensor is going to be the identity matrix. So then in that case, then we have the nonlocal dilatation formulation is going to recover the original nonlocal dilatation formulation from the LPS model. So that means this formulation for the nonlocal dilatation is actually a unifying framework, unifying formulation for the whole region, for both the green region and the red region. So okay, yeah. So now we know that this correction tensor is going to be identity matrix when it's inside. But what about when it's in the red region? Is that so? One of the maybe first question is this well defined? Does this inverse of this matrix exist? So here is what we try to justify mathematically. So we can show that as far as our domain has sufficient smoothness, that means it's C3, then this correction tensor is well defined, and our modified dilatation is also well defined. And moreover, we can show that when when we have a C1 solution U, then we can show that this corrected non-local dilatation is still consistent with the local dilatation. So that means basically it's going to converge to the local dilatation with a first order in delta. So that is for the non-local dilatation. What about the momentum balance equation? So for the momentum balance equation, let's still take a look at what's happening when a material point is outside, it's nearby the boundary. So what is the missing part is basically so when we do the integration, we don't know what is the interaction between these material points and the material points in this yellow region. So those interactions are missing. So therefore, we want to provide an approximation for those interactions. So that is given by this red term here, red expression here. So our idea is we use the nice property of peridynamics of the LPS model that it's corresponding with the linear elastic model, and then we use the Taylor expansion. So then finally we propose these three terms as the approximation for this missing interaction with the material outside. So if you look into these three red terms, the additional terms. So firstly, on the left-hand side, we notice that it's given by it's actually given by a parameter A and multiplying with the non-local dilatation. So here we notice that both for the non-local dilatation and for the displacement. So we only use the material points inside the computational domain omega. So that means no extension, no extrusion will be required for this method. And on the other hand, what about the right-hand side? The right-hand side, we separate the traction load onto the tangential and the normal direction. And here we assume that this traction load, we only use the traction loading on the shaft interface. So, and then this so this loading, we can see that they are multiplying with some parameters, and these parameters, they are going to vanish when we go to the interior of the domain. I mean, when the distance is away from a distance of delta. So that is kind of similar to the idea that described by Patrick and Dr. Rob Lipton yesterday. So that the traction loading is applied as kind of a body load on a thin layer of the boundary. But the difference here is our coefficient, they are going to vanish, smoothly vanish when it goes to the inside of the domain. So therefore, for the whole, when we try to look at a material point that is like away from the boundary, then we are going to see that all these integral, like the represented by orange here, they are going to vanish. So therefore, these three additional terms, they are going to vanish. So therefore, in that way, this formulation also gives us a unifying formulation for all the material points. It can describe the scenario both inside the domain and near the boundary. So okay, so yeah, so that is the basically, finally, we get a unifying non-local framework on the whole domain, a non-local description of on the whole domain. So it can handle not only so it can handle the regions with or without damage, and also when it's near the traction loading or when it's far away from the traction loading. And on the other hand, when there is a fracture, when there is an evolution of the fracture and the corresponding evolution of the domain, how should we handle that? So here from the formulation, we notice that all we need to handle is the change of the integration region. So basically the blue part here and the orange part here. So yeah, so later we are going to see that this can be naturally represented by the Meshfree quadrature rule we provide. So okay, so now let's look into some properties of these mathematical properties that we can prove for this traction loading formulation. So the first thing we notice is this traction loading when the boundary has sufficient symmetry. So that means when the horizon near the boundary is symmetric with respect to the normal direction, then it passes the linear patch test. Otherwise, it's going to pass the linear patch test approximately, so by a difference of delta. So and then we also try to check the truncation estimate. So for the truncation estimate when it's nearby the boundary, so basically when it's in the red region here, then we have a O1 truncation estimate. So this O1 truncation estimate, although it sounds scary, but I want to add two comments about that. So firstly, from our previous study on the nonlocal diffusion equation, we found we can prove that this O1 truncation estimate is actually going to give us an O delta convergence in the L to none to the corresponding local limit. So therefore, the formulation will still be asymptotically compatible. And then on the other hand, later when we discuss the Meshfree quadrature rule, we are going to see that actually this O1 truncation estimate is already the best we can get, because we are going to get another O1 truncation estimate from the bound breaking representation of the boundary. So okay, so now we are looking into the discretization method. We want to develop a Meshfree quadrature rule to discretize the LPS model we propose. So basically, all the integral are actually represented by a one-point quadrature rule. So how do we generate the quadrature weights? Here we use the idea of the optimization-based quadrature rule. So for each of the discretization point, we solve in the pre-processing step, we solve for a local optimization problem, and then we generate this quadrature rule such that to make sure that this integral is accurate for a group of functions. So here for this group, for the LPS model specifically, we hope that it's accurate for the quintic function, of quintic polynomial divided by y minus x to the cube. So why is that? Because we can prove that as far as we have a full horizon, like in the domain, then this type of the discretization method is going to give us O delta truncation error for all the nonlocal operators in the LPS model. But then the question is, what if we don't have a full horizon, or when there is a damage, when the material point is actually near the traction loading boundary, or when there is a damage, the fracture occurs, what will happen? So here is what we are going to do. We are going to the fracture surface is going to represent it by breaking bonds. So basically, we assume that for each material point nearby the boundary, when its interaction with the material points outside the domain, it's actually we say that those are we break the bonds between those material points, and then material points pairs. And then for the material points still inside the domain and also in its horizon, we say that they still have unbroken or intact bonds. So then we separate the quadrature weights we generated into two groups. So the first group is by what we represented by blue here. So that represents the quadrature weights associated with the unbroken bonds, and the part of the quadrature weights represented by orange here are the quadrature weights associated with broken bonds. And then when we try to estimate the integrals in our formulation for inside the domain and outside domain, we use these two groups of the quadrature weights respectively. And then here I want to emphasize that when there is an evolution of the fracture, and then there is a change of the region for the blue region and the orange region, we don't need to regenerate the quadrature weights. All we need to do is to cut some of the unbroken bonds into broken and move the corresponding quadrature weights from blue to yellow. So yeah, so therefore, this way we have efficient, kind of really easy handling of the evolution of the fracture and also the newly formed boundary. So, but however, it also has some drawback. So the drawback is this way we can see that all the geometry, all the boundary, we never know what is the real geometry of the boundary. So the real geometry is actually represented by those broken bonds. So that means this method, we wouldn't be able to tell the difference between this red boundary here and the black boundary here. So actually, we can show that this way, this type of the handling of the boundary by the broken bonds in the Meshfree method is going to also create some geometric error, and this geometric error is going to introduce an O1 truncation estimate also for the points near the boundary. So that's why I said that the traction loading, the truncation estimate from our traction loading formulation is already optimal, because that is the best we can get by this bound breaking way to represent the real geometry. So, and also as we discussed before, we can still expect, and we are going to verify that we still have the asymptotic O delta asymptotic compatibility in the L2 norm. So, okay, so now let's, before we run into the experiment, let's try to review some of the properties of this proposed traction loading formulation, and then we are going to emphasize those properties highlighted by red in our numerical simulations. So firstly, we have no restriction on the dimension, and so therefore we are going to show the experiments in 2D, but it can be applied to 3D. So then also the whole formulation is nonlocal. So that means the crack can initiate on boundary. And also we have no restriction on the discretization. So we are going to investigate both the uniform and the non-uniform discretizations. So, and then it can also, we are also going to investigate its performance on both complex loading on complex geometry. So such as the curved boundary or the boundary with corners. And then lastly, we are going to show some validation on handling the brittle fracture and also the evolution of the fracture. So yeah, so then firstly, let's look at a case that with the analytical local limit. So we have a square domain and we apply the traction load on the top of the surface. So in this, so then here we try to compare the difference between our non-local numerical solution and the analytical local limit, and then we try to keep the ratio between the delta and the discretization size. So here on the left-hand side, we show the results from the uniform discretization. On the right-hand side, we show the results from non-uniform discretization by perturbing the uniform discretization, the grids by 20%. So here we perturb that, so here the perturbation satisfies basically a uniform distribution. So we set this perturbation like randomly. So here here we can see that for both the uniform discretization and the non-uniform discretization, we achieve like a first order convergence to the local limit. So that's why I say it's still asymptotic compatible and with the O delta convergence, and also both for the compressible material and nearly incompressible material. So now let's look into some scenarios that not kind of discussed like in our mathematical proof. So that is when our boundary is not C3, it's not smooth, when we have a Lipschitz boundary. So in this case, we consider the case that there is a corner in the boundary. So then the normal direction is undefined when it's close to the corner. So therefore, we use a numerical approximation to the normal direction for our formulation. So here we can see that for the uniform and the non-uniform discretization, we still get roughly first order convergence. So then another example is for the curvilinear surface. So when we have a hollow disk which is subjected to the interior pressure inside, and then we try to compare our solution with the analytical local solution and to check our formulation in handling the curvilinear interface. So yeah, and finally we still get first order convergence for all the cases to the local limit. So now let's look into some validation. So let's try to investigate how is the performance of this workflow on brittle fracture, on the dynamic brittle fracture. So the first case we consider is a benchmark dynamic crack propagation problem, which was investigated by Dr. Ha and Bavaru in 2010. So this is a pre-notched soda line glass, and we have the stretching on the top and the bottom of that. So then we are going to, okay, can you guys see this video? Yes. Okay, so basically we have we are going to have the crack growing on the top of the notch tip, and then it's going to go bifurcating and finally reach the right side. So here we try to quantitatively compare the some of the benchmark quantities, so including the bifurcation location and and also the propagation speed of the branching. So here we can see that for all the quantities, we match quite well from the literature in both experiments and the simulation, except the maximum propagation speed. But however, we think that's probably because we didn't use sufficiently refined discretization, because when we refine our discretization and the horizon size, we get the value closer to the maximum propagation speed. So then another interesting property we want to investigate is, again, the non-uniform discretization. We want to see if our simulation is reproducible when we have the non-uniform discretization. So here, on the left-hand side, we show the results, the damage map from the uniform discretization, and the right-hand side is the damage map from the non-uniform discretization by perturbing our uniform discretization by 20%. So here we compare the results from 3 different quadrature rules. So the first one is from the so-called Riemann sum. So when we use the uniform quadrature rule, so we can see that when we go into the non-uniform discretization, it doesn't give us the kind of the consistent damage map. But when the second method is the Delaunay quadrature rule, so you need to generate the triangular mesh, and then this quadrature rule is basically the area of each of the triangle. So it requires some meshing, but however, it also give the consistent the damage map when using non-uniform discretization. And lastly is our method. Our method can also the damage map is also reproducible. So then the other experiment I want to show is some comparison with a recent experiment to try to reproduce a recent experiment on the V-notch glass sample, which is impacted by a striker. So the setup of the experiment is as following. So the nice part of this experiment is they provide also what are the normal force, like applying on this striker. And in this experiment, three prevalent optical techniques was applied to 3 different samples. So like as listed here. So basically in these 3 samples, what they observe is the branching location is actually goes from 53% to 56%, and the branching angle is in the range of 55 degree to 69 degree. So now we want to see if our simulation with the normal force measured from the experiment and also with the same material property, can we reproduce the damage pattern? So here, there is one detail which was not provided by the experiment. So that is the shape of this striker. So we can see that this striker doesn't contact with the whole V-notch. But in our first but we don't know what is the exact shape. So in our first simulation, we assume that it has a fully contact with the whole V-notch. And here is a movie from our simulation. So we can see that this crack initiates, and then finally the crack propagation speed reaches maximum when it goes to bifurcation, and finally it gets lower, and also it also gives us the wrinkle that when it gets closer to the right hand side, and this wrinkle was also observed in the experiment, in all experimental samples. So, and now let's compare the values quantitatively. We can see that for our method, our simulation kind of predicts the branching angle as 58 degree, and so that is consistent with the experiment. But the branching location is a bit further than the experiment. So then we realize that's probably because we use the assumption of the full V-notch. So therefore, we run simulation on partial V-notch. We can see that we get more consistent the branching location. And on the right-hand side, I also compared these results with some of the results from the state-of-the-art the methods, so including the bond-based peridynamics model, the phase field model, and the LS-DYNA. So although I wouldn't say that's a super fair comparison because they don't have the normal contact force measurement available, However, we can see that we have the best prediction on the bifurcation angle comparing with all those methods. So yeah, and again, oh sorry, I'm too slow. Okay, yeah, and also we verify the reproducibility when using the non-uniform discretization method, and also we can see that our bifurcation angle and the bifurcation location is quite reproducible for non-uniform mesh. Okay, yeah, so more details of this work is actually already submitted and can be found in this paper here. So I'm going to finish here.